supposed to be on. So let's just wait for a minute. Wait for a minute. Then we should be maybe run out of bundles. Let me just check. I think we can start. So Sangachi, you have 2 MBs. Okay. Just check something. Okay. In 5 minutes. Okay. Don't know how I'm going to wrap this. Before I can spirits. Ako bozo shops. Aba kwa tatma baba shops. Gentlemen, bara shisha spirits pamako bozo shops. Bara shisha spirits. M1, M2. Okay. Let me just check. It's supposed to automatically show that we are live. Okay. Check on your portals. It's supposed to show. Just check so that we can give a green light to those who are not here. Look, 2, 4. That's okay. Is it showing that we are live? And the sound. So check the sound. Just need some spirit here. Is it showing? It's showing. How is the sound? Check if I'm audible, because I might not be audible. Just check. Tell me if I'm audible enough. Is there anyone who can rush to Kobusu shops and buy spirit so that we can clean the boat? Is there anyone? Leonard, taarifa huko kutoka ko. Right. Ufike kwa Kobusu shops. Because I need to fix the live stream before anything. So for the awareness, everything is working. Is it okay? Okay. Spirits so that we can clean the boards. Okay. Watch. Or maybe I can just share the link. Okay, we'll be starting around 16:30. Okay, so we are doing statics and dynamics. Statics and dynamics. Okay. Share. Okay. Can you kindly check if the link is working? That link that I've shared in the group. CHPH. It's working? The link, is it working? The link that I've shared in the group for the live stream. It's working? The sound, how is the sound? Okay. Yeah, even better. It's loud, eh? Okay. At least the sound is now clear. We can start. Let's tomorrow later, guys. Yes. What's bothering you in physics? PH. What's bothering you? Nishi shupa, so that we can fix it. What's bothering you in PH? I can open this one. Oh, statics. To be specific, statics. If you will statics. Eh? Yes, where are you having problems or challenges? Do you have any challenges? Or what kind of questions are giving you challenges? Okay, just make a voice note in the group. Okay, so I will start from scratch. We are going to start from the very top. Okay, what is statics? What is dynamics? We do some very important questions. Okay, tricky and important questions. Okay, so let me just do this. Right. Statics and dynamics. Let's just wait for about a minute or two before you can start. Okay? Because I need to wrap this part. Yes, where are you having challenges? Statics and dynamics. At what is statics? What is dynamics? Ninshile shup. Mamundo ninshile shup. You never question. Tutorial sheet one push up sanga. Masanga pano kufishwa vyonzi vya mu tutorial sheet. You need to know. You need to know everything in the tutorial sheet. Mwaisanga in the tutorial sheet. Kamuna sanga. Your tutors, have they given you the answers? I am the entire tutorial. Okay. Thank you very much. Thank you very much. Right. Spirits. What is what one with? I. What I know if people are crafty sometimes. They can drink anything. They do drink anything. Bah. I'm no from nowhere. People used to drink this. I don't know if they still do. People drink this, they would become drunk because this is alcohol. There is alcohol in here. Okay, there's alcohol, so people consume it for unknown reasons. I think I have this. Okay, so we'll be starting very soon. Just clear the board. Sorry. Resurrected spirit reminds me of biology. Testing for starch. Did you do testing for starch in biology, part 12? where you would boil the leaf in some alcohol to remove the chlorophyll. Okay, that's better. All right, let us start. Okay, so here's the thing. What you need to know in statics and dynamics is that, well, most of the questions will not, most of the questions will be very similar to what you have in the tutorial sheet, right? Will be very, very similar. So PH 110 will be very similar to what you have in the tutorial sheet. So my first advice is you need to know how to answer each and every question in that tutorial sheet of yours. Make sure that you know how to answer each and every question. Okay? Right. Okay. So statics and dynamics. We had the lesson. I don't know if I don't know which was it last week? Yeah, should be the other week. We had the lesson where we did some statics and dynamics. We did a few questions here and there from a certain paper. Now I will start from scratch. Okay. So here's the thing. We have two principles, which is the first one is statics and the other one is dynamics. Okay. So you need to know the difference between these two, statics and dynamics. From the word static, that's where if you have something, okay, let's say you have a ball, okay, if you have a ball and it's on the ground like that, and this thing is not moving, it's not going anywhere, okay, it means that this thing is static. Okay, so if this thing is not moving, it means that it will be what? Static. And what will be the acceleration? If something is moving, we say that acceleration is the what? The change in velocity, right? Yeah. So because this thing is moving, is not moving, it means that the velocity, the change in velocity is what? Is equal to zero, meaning that even the acceleration will be equal to what? Will be equal to zero because this thing is not moving. So the word static means that something isn't moving. Is it okay? So the other concept now is, let's say this boy is kicked, okay? This boy is now kicked. So we have someone who has kicked this ball, and now this thing is moving at a certain velocity, meaning that there is a change in velocity and acceleration will be equal to a certain number. Okay, so we are going to have acceleration here. We're going to have acceleration. It will be equal to a certain number here. Okay, so it will be equal to anything greater than zero. So acceleration will be, you can say it will be greater than zero like this. So if you kick this ball, it means that since this thing is moving, we are going to say that this thing is what? Is dynamic. Okay? So these are the two principles. Okay? If you understand this one, then it will be very easy for you to understand the future concepts. So this and these principles that you learn now will be applicable to this term. Okay? Because you still have to resolve some courses. Okay, when we start dealing with work energy and power, you still need these concepts. So it's very important for you to differentiate between what's static and what's dynamic. Get the point, right? So if this boy is here, it's moving, it's just on this on the ground. Let's say this is the ground. Okay, If this is the ground and we have the ball there, there should be a balance of forces, okay? Because if there is no balance in terms of forces acting on this ball, you find that this ball is supposed to move, okay? So you find that the first one is, the first force will be the weight of this ball, okay? Let me draw it here. So this ball has weight, which is W, which is equal to mass times G, like this, all right? So now, if this ball, let's say it's in the air, in which direction will this thing go? In which direction? Is it up or down? Eh? Down. Not up. Not sideways. In which direction? It will be down because the force is pulling it downwards. Okay? So you have to look at the direction of the force. This direction of the force will tell you the direction in which the object will move. Get the point, right? Yes. So this thing will move down. Okay? Now, because here it's in thin air, okay, so it will move down. What if it's on the ground like this and this mass and the gravity is still acting on this? What's going to happen here? We are still going to have what? We are still going to have mg, right? Okay, but for this thing not to move, because if there is no balance in terms of forces, for this thing not to move here, it means that there is another force which is counteracting on this force, meaning that this force should be going in the opposite direction for this thing to stay where it is. Get the point, right? Yes. Because here we said there is no ground here, right? So if only the weight is acting on this, it means that this thing will be put downwards, right? Now on the ground here, and the weight is still the same, why is it not going downwards? It's because the surface, the ground that we have here, is also applying a force on the ball. Get it, right? So that force is what we call the normal force. Okay? So whenever you have something on the surface, okay, you have something on the surface, I have this, then I put this marker here. For this not to move here, it means that there are forces which are balancing up. Okay, so the force, this weight that we have is equal to that other weight. This is why this ball is not moving. Let's say I remove this mg and I only remain with this normal force. Where do you expect the ball to go? Is this still going to be the same? Or is it going to be on the ground? Let's say there is no weight here. I remove this weight that you see here. I remove this mg and there is only this force. Where do you expect the ball to go? Where? It will go where? It will go upwards because only this force is acting on it. Okay? So depending on the direction of the force, okay, depending on the direction of the force, that's where the object will go. So in this case, for this ball, which is on the ground, for it not to move, there should be two forces. Number one is the weight, and the other one is the normal force. So the normal force is a force which is always applied by a surface where this object is. For example, if we have this, okay, I have a block here, or I can have something like this. I have a block, all right? So in this case, because this is the surface here, this is an incline. Because this is the surface, remember this is the surface, right? So this surface will always be applying a force on this block, and this force is what we normally put here as the normal force. Get the point, right? Yes. Again, for this one, because this is the surface here, this is the surface here, then we are going to have the normal force applied by what? By this thing. So it will be going upwards. Okay? Again, because this object has mass, there should be weight which will be acting on this object. So this normally comes from the center. Okay? Let's say this is the center of mass, so it will go like that. Then we are going to have our mg like that one. Okay? So because these two are balancing up, this is equal to that, then this thing won't move. Get the point, right? Even for this one. Okay? Do you expect this thing to move? Is it going to move? Is it going to move? If I put a pen here, is it going to move? Because this is an incline. It's going to move, right? Yes. So it means that there is an imbalance in terms of what? Of the forces. Okay. So how can we show that imbalance in terms of forces? You can do this. Remember that there's the normal force, right? Then there's also this force. Whenever we have an incline like that one, it's either this object can go this way or the other way. Okay. So here we are going to have what? We are going to have the weights. Get it, right? Now, again, we can resolve this. we can resolve it into two components. Okay, so we can have this component and this other component of the same weight. Okay, so weight is equal to what? Mg. So this angle that we have here is supposed to be equal to that angle. Okay, so because this is opposite, then this will be mg sine what? Sine theta. Then this one will be mg cos what? Cos theta. This is how we come up with that. Get the point, right? Yes. So in this case, have you seen the imbalance in terms of forces? Have you seen the imbalance? Let's say we have the x, y plane here. We have the x and the y, like that. We tilt our heads. There is this force, the normal force, which is, what's the opposite of the normal force? We have this force, right? Now, there is also this force. Now here, what you have to concentrate on will be these, the resolved forces, okay? So you forget about this one because you have resolved it in terms of the x and the y. So going in this direction like that one, you see mg sine theta. Is there any force this way? So where do you expect this thing to go? Because there's a balance here, it won't move up or down, so it will slide, go in there, because this is the only force which will be active. All these forces are acting there, but this force is not balanced because there is no force counteracting that other force. Get the point, right? So now, if this thing is moving, going downwards, what can we do in order for this to stop? What can we do if you are following? If in order for this to stop, it's moving. Now, if we want to stop here, we can pull here, right? Let's say we pull with the force F, and this force is equal to that. So if this is equal to that, it means that this thing won't move, right? Yes. So now, what usually happens when you have an incline like this one, you will have what we call friction, right? You know, by now you should know what friction is. We have two kinds of friction. What are the two kinds of friction that we have? Static and static friction. We have static friction, and we have the kinetic. Okay, so we have these two, the first one and the second one. Okay, so now here you have to know where to apply these two, the static and the kinetic what? Friction. Okay, we can say this one is Fk, then this one is Fs. S for static, K for kinetic. Get the point, right? Yes. So in this case, remember that Fs is equal to mu s what? What are we supposed to have here? N, right? Then we have Fk is equal to mu k. We have N. So these are the formulas that we are going to be using when you are dealing with what? With friction. How does friction come in? Friction comes in whenever an object is moving on a surface. You get it? So if I have an incline like this one, I expect some friction. Okay? So we can say this force here, there's a force acting going in the other direction. If this thing is moving in this direction, it means that the friction will always try to oppose where this object is hitting, meaning that the friction will always go in the other direction so that there is a balance, right? So here we can have, if this thing is moving, we are going to have kinetic friction. If this thing is not moving, okay, we are going to have what? Static friction. So we can either have K or S. We can either have, for a moving object like this one, if it's moving, going downwards like that one, it means that this is what? This is dynamics, okay? And we have to apply what? Fk. If it's not moving, it means that we are going to apply what? Fs. Get the point, right? You get the point? Hey, ask questions. Do you have any questions? Or no questions? No questions. We can move, huh? Yes. Yes, there is one. Yes, please. You can ask. Static friction. It's this one. Mu s, the coefficient of static friction multiplied by the normal force. You get it, right? Yes. So whenever we want to find, for example, we have friction. Friction, let's say this object is moving in this direction. It's moving, the acceleration is moving like that. If this object is moving like that, the friction is supposed to be opposing the direction in which this object is moving. So we expect the friction to be where? To be here. So Fk. If it's moving, we use Fk. If it's not moving, we use Fs. You get the difference, right? Yes. Now, how do you find this? What's the formula for Fk, for friction? This is why we are saying Fk is equal to mu k what? N, like that. Or if it's not moving, and they've told you that there is friction there, okay? Because even if something is not moving, you can still have friction there. Get the point? So let's say the friction, okay, let's say we have this force. This force is, let's say, 10 newtons. Then we have some friction here, which is also 10 newtons. Do you expect this thing to move? No. Okay, because these two forces are the same. And if these two forces are the same, it means that what's acting here is static friction. Static friction applies when we don't have any movements there. Okay? Yes. So these are the two formulas that you are supposed to use. So mu what? Mu S N. Get the point, right? Yes. So those are the two. Now, apart from this one, so I've given you two scenarios here. I've given you two scenarios. Number one, where you are supposed to have your mu k there, okay? In the question, they are going to give you mu k, okay, which is the coefficient of kinetic friction or the coefficient of static friction. If they haven't given you, it means that somewhere you are expected to find this. Get the point, right? Yeah. So whenever you are dealing with statics and dynamics, you are supposed to keep this in mind. Get the point, right? Now, remember that statics deals with something which is moving, and statics deals with something which is static, not moving. All right? So let's say you have a system. Remember that question in your tutorial sheet? How is it? Is it like this? This question. Remember it? Is it like this? Yeah. So you have two masses. Let's say you have mass 1. You also have mass 2, right? You have two masses like this one. And then they will tell you that this is in equilibrium, okay? Equilibrium. So what are you supposed to do in such a case, okay? Because this thing is not moving. What do you expect? Is it a dynamics equation or a statics equation? Or question? It's static because it's not moving. So in this case, what are you supposed to do if you have such? You can cut this and make it into two systems. So you are going to have this system, system A, then you are going to have this one as your system what? B. Then you can answer them. You can answer this one, deal with this alone, even that one, okay? Sometimes it will give you simultaneous equations and answer them like that. Now, here, what you have to understand is that whenever you are dealing with this, there will be a balance in terms of forces, okay? Whenever you are dealing with something which is static, something which is not moving, it means that how forces now balance. There is a balance in forces. Now, how can forces balance in this way? Okay. For example, I will come back to this. If this thing is not moving and we have the weight and the normal force, if these two, okay, if this thing is moving, it means that these two are what? Are balanced. Get the point, right? Yes. So that's static, right? So even in this case, whereby you have a bunch of ropes, you've been given some ropes like that one, we are going to still apply the same concept. It's just the diagram which will be different. Get the point, right? So that's what we are going to start with. Okay, we are going to start with this one. And here's the question. It's coming from a question paper. You can write this question so that we can do that one because it's in your tutorial sheet. The question that we are going to do is coming from a question paper session, or it was 8 marks. It's similar to what is in your tutorial sheet. Okay, so once you just understand this, I want us to start with statics, then we can go to dynamics. Okay, but there are two important questions that I want us to tackle. Okay, can I rub this? Should I rub? Yeah. Right. I can rub? Right. Let me rub this. This mark. What's wrong with it? I think I'll stop using it. It's not okay. It writes well, but I can't rub effectively. Unfortunately. All right. So here's the question. Here's the question. I'm going to read it. The question says, a traffic light weighing 100 newtons, a traffic light weighing 100 newtons, hangs from a cable tied to two other cables. A traffic light weighing 100 newtons, so it's weighing, we have a light, a traffic light weighing 100 newtons. Here we have a traffic light here. So there, this is what we have. So the question continues. A traffic light weighing 100 newtons hangs from a cable tied to two other cables, fastened to a support. Fastened. Okay. 100 newtons hangs from a cable tied to two other cables, fastened to a support, as shown in figure 3.2. Okay. As shown in figure 3.2. The upper cables make angles of 37.0 degrees. So we have this. I'm supposed to use this mark, though it will give me a headache when rubbing. So here we have 37.0 degrees. Then here we have 53.0 degrees. Right. So the upper cables make angles of 37 degrees and 53 degrees with the horizontal. If the system is in equilibrium, find the tension T1, T2, and T3. So we have T1, T2, and T3. Okay. I was going through your tutorial sheet and I saw such a question whereby there was a bag of cement here, right? Tutorial sheet. Or maybe don't be done with the tutorial sheet. You're supposed to make sure that you go through that tutorial sheet. There was like a bag of cement, or maybe the tutorial sheet here in Nachama. Eh? The question, let me repeat. Okay, the question is saying, a traffic light weighing 100 newtons hangs from a cable tied to two other cables, fastened to a support as shown in figure 3.2. So that's figure 3.2. Okay, the upper cables make angles of 37 degrees and 53 degrees with the horizontal. Full stop. If the system is in equilibrium, find the tensions T1, T2, and T3 in the cables. Okay, so this is the figure that we have. Now we are asked to find T1, T2, and T3. All right. Now let us start. And it's 8 marks. This same question for you to find those. They were given 8 marks. Okay. So let us start. Ideas. How are we going to handle such a question? This is something, number one, there is equilibrium there. Equilibrium. Okay. So how are we going to handle such a question? We are supposed to find T1, T2, and T3. How are we going to handle it? How? Huh? Yeah, you can identify the joints. Okay, where are these ropes joining each other from? It's here, right? Okay, so you can take that part because you are here. So there is this one, there is the other one, then there is another one, like that. You have the first tension. Okay, you have this rope. So there is tension in this rope. So you are going to label it as T1. And whenever you are writing forces, they will go away from this joint that we have here. So they will go away like that. Okay. So this is what we are going to have. Your T1 pointing there. Then you have your T2. Then you have your T3. You get the point, right? So this is where you're supposed to start from. Okay. Now, according to what we've been given this. Okay. What was the question saying? It has given us some information. Let us try to collect the data first. Okay. So this is the free body diagram that we have first. Okay. So whenever you are dealing with statistics and dynamics, a free body diagram is very important. Okay. You are always supposed to write or to draw a free body diagram like this one. Okay. So you just look at what you have and try to translate it into a free body diagram, and you get a mark. Okay? So the question is saying, I'm going to repeat, a traffic light weighing 100 newtons. So the weight for this weight is 100 what? Newtons. Okay? And we have some cables there. Then the question is saying, if the system is in equilibrium, find the tension T1, T2, T3. So we have T1, T2, and T3. We have been given these angles here. So the secret, when it comes to such questions, all you have to do is you have to resolve what you have. You resolve them in two components. Okay? So in short, remember that your XY plane is like this, right? So you have to resolve whichever is not in line with the XY plane. This one is in line with the Y-axis, right? So we can't resolve this one. What we resolve are these things at angles. Get the point, right? Yes. Now here, remember those angle properties that you learned back grade 12. They are very important. That's why you learned them. They are back. What you have to do here is you have to find the angles, okay, at this point and at that point. Get it right? So if you have such, if you've been given this angle, it means that it's equal to that angle. Is it true? Yes. So if this is 37.0, it means that even this one will be 37.0 degrees. That one. If this is 53, according to angle properties, this should also be 53.0 degrees, like that. After you identify these angles, then you can now resolve them. So you can resolve this. Now we are here, right? So here's the horizontal. So we have the horizontal like that. Okay? Now you have to put your angles there. So your angles will be, we have this one and we also have this one. This one is 37, then that one is 53. So meaning that if I resolve this one, I can actually resolve it like that. Even this one, I can resolve it like that. Okay? So if I resolve this, what am I going to have? I'm going to have T1 what? Is it cos or sine? There. It's going to be what? It's going to be sine. Because this one, opposite. Remember, SOHCAHTOA. We are still using SOHCAHTOA, right? Opposite, the hypotenuse is T1. Now we are looking at the opposite, which is this one. So we are going to say T1 sine what? Sine 37. Okay? Even this one now will be T1 cos what? Cos 37, like that. We do the same thing for this one, even that one. So this one, because this is T2, so it will be T2 what? Sine what? Sine, we have 53, right? This one will be T2 cos 53 degrees. You get the point, right? So once you do this, then the next part will be to see what you have in the y-axis and what you have in the x-axis. Okay, so summation of all the forces, because this is in equilibrium, there should be a balance, right? So the forces going upwards and the forces going downwards should be the same. Okay, should be equal. The forces going to the right, the forces going to the left should be equal. Get the point, right? So in this case, if we are dealing with the x-axis, because this is the x-axis, okay, all the forces here are supposed to be equal to 0. So meaning that the forces going this direction and the forces going in that other direction are equal, right? Are equal. So we are going to say T1 cos 37 should be equal to what? T2 cos 53 degrees. Get the point, right? Yes. So in other cases, or you can say T1 cos 37 minus T2 cos 53 degrees is equal to 0. This is the same thing. Okay. So even if you say this minus this, your answer should be what? Should be 0. Okay. So for just easier understanding, and when you are working out for everything to be easy, if this is in equilibrium, what you have to do is just say the forces on this side should be equal to the forces on the other side. The forces going up should be equal to the forces going down. That's the concept. All right. So in this case, what we have here, what do we have? We are saying the T1 cos 37 should be equal to the T2 cos what? 53. This is the statement that we have here. As simple as that. You keep it like that one. Okay? Because we have two unknowns. We have T1, then we have T2. Now, the next thing will be, remember that our weight here is what? Is 100 newtons, right? Yes. So if this is 100 newtons, it means that the force going downwards there is what? 100 newtons. So it means that your T3 is what? Supposed to be 100 newtons. Okay? So T3 was given there, and in the question it was given to say, can you find T3? So we've found T3. We are just remaining with T1 and what? T2, right? So let us go to the, after you are done with the Y forces, or with the X forces, go to the Y forces. Now again, there is equilibrium there. Okay, I'm going to write here. So we are going to say, whatever you have in the Y, whatever is going up should be equal to whatever is going down, right? So what do we have going up? We have T1 sine 37. So we have T1 sine what? 37. Okay, we have this. T1 sine 37. Now we have two forces going upwards. So we have T1 sine 37 and T2 sine what? 53. So it will be plus T what? T2 sine 53 should be equal to the forces going where? Down. What are the forces going down? It's T3. What's T3? It's 100 newtons. So we are going to have 100 like this. So this will be our second equation. Then this is our first equation. So basically we have two unknowns. We have T1 and T2. Even in this one, we have T1 and T2. So we can solve these two simultaneously and get our answers. Okay? Any questions? Any questions? Do we have any questions? There is no question. Yeah. Thank you. It's supposed to be summation of forces in the Y. So you're supposed to also to always indicate that there's a summation of the forces that you have in the Y-axis. So these supposed to be equal to 0, meaning that whatever you have upwards, going upwards, should be equal to what you have going downwards. So this is the statement. So you're supposed to also include that one, the way we did it here. So we have two equations that we can answer or solve simultaneously. So let us solve. So we have T1 cos what? Cos 37. Then this guy can go to the other side, right? So it will be T2 cos 53, which is equal to 0. So we can solve simultaneously. Solve simultaneously. Okay. You have 2 minutes to solve simultaneously. Can you solve that one? Solve it. Any simultaneous equations that you'll be having, like this one, okay, they have such a simultaneous equation. So it's also a good idea to punch this. You can also punch sine 37. You can punch it if you want, so that you can have a value. You can have a value, or even just from here, you can use substitution method. It will be the easiest in this case. You can just make, let's say, T1 the subject of the formula, then you are able to substitute in there, then you can find your T1, okay, then you can find your T2. So you can use substitution. If applicable, you can also use, what's this? Elimination method. Also able to do that. Yeah. But you can use elimination method if you have dealt with this sine 37, cos 37, and the like. You're able to deal with it. If you have dealt with that, then it will be easy for you to deal with this. Okay. So what are we having? What are we having? What are we having as our final answer? What are we having as our final answer? Or maybe we should do it together. But still, I'm going to give you 2 minutes. You have 2 minutes to answer that one. What are we having for T1? What are we having for T1? What are we having for T1? What are we having? Let us solve. Okay, let us make T1 the subject. So what are we going to have if we make T1 the subject to the formula? If we make T1 the subject to the formula, or maybe which one do you want? Do you want us to just be taking these with us, or we punch them? We punch them. Okay. So sine 37, what's sine 37? 0.6 what? That's all? 60. 60. That's all? Or there are some numbers still? Sine 37. What are we getting? 0.60 what? 18. Okay, let us do it correct to two decimals. Okay, 0.61, right? 0.61. So we have this one will be T1, then we have plus. T2 sine, so we have sine 53 here. What's sine 53? Correct to two decimal places, just two decimals to make our lives easier. What are we going to do? Here, sine 53 is what? What's sine 53? Sine 53 is 0.7986. Okay, so let us say 0.7, we can say 0.80. Then we are going to say this is our T2, which will be equal to 100. Let us also deal with this one. What's cos 37? What's cos 37? T1 minus, here we have T2 is equal to 0. What's cos 37? Cos 37? 0.80. Then the other one, cos 53. Cos 53. What are we getting for cos 53? 0.60 after 0. There's one. Okay, so we can end here. Okay, so from here, let us make T1 the subject to the formula. So T1 will be equal to, so we have 100 minus, this guy can go to the other side, right? So 0.80. Then we have our T2. Then we can say divided by this entire thing, 0. Let me see. Okay, 61. Are you agreeing with this? Do you get what I've done here? We have three equations. So I've made T1 the subject to the formula. What did I do? This 0.80 T2 goes to the other side, which is 100 minus what? Minus this. So 100 minus 0.80 T2. Then if this has gone to the other side, then here we are remaining with 0.61. We are supposed to divide both sides, right? So in this case, we are going to have 0.61 down here. So now we can substitute this equation, we can substitute it in there. So we are going to have this. Going to have 0.80, then 100 minus 0.80T2 divided by 0.61 minus 0.60T2, which will be equal to 0. It would have been easier if we just took this one, equation number 2, instead of equation number 1. But the answer will still be the same. Okay, what are we going to have? What are we going to have? What are we having? We have substituted. Now we can say, so we have this. So we can multiply this throughout, right? Or maybe let us get rid of this. We can get rid of that by doing what? By doing this. 0.80 divided by 0.61 is what? Let us get rid of this. You can put it in front there. What are we getting? 1.311. Just 1. Okay, we can end here. So 1.31, then inside here we are going to have this 0.80 T2. Okay, minus 0.60 T2 is equal to 0. Then now we can distribute this multiplied by that, also this multiplied by that. What are we getting? What are we getting? If we say 1.31 divided by multiplied by 100 is what? Multiplied by 100. 1.31 multiplied by 100. What are we getting? 131 minus 1.31 multiplied by 0.80. What are we getting? 1.048. 1.048. Then we have what? T2 minus 0.602 T2, which is equal to 0. So we are able to now see the like terms, right? The like terms. These are the like terms that we have. Okay, we have this one, negative 1.048 T2 minus 0.60 T2. Can you add these two? What are you getting? When you add those two, what are you getting? What are we getting? Yes, what are we getting? Here, 1.048 plus 0.60. Remember, if you have both negatives here, you can easily add them. So what are we getting? So what? 1 point what? Okay. 1.648. So 648 T2. Okay. So since this is negative, I can take the entire negative to the other side and it becomes positive. So I'm going to have this divided by 1.648 divided by 1.648. What are we getting? T2 will be equal to what? 131 divided by 1.648. What are we getting? What are we getting? If you divide here, what are we getting? 79.490. So this will be our T2. We have answered T2. So from this equation, this T2 that you see here is 79.49. Like that. Let us go to the other one. Any questions before we can move? Any questions? No questions. Any question? No question. You have understood what's happening here, right? You haven't. Why? So we started from here. Okay? We have this system. You have rope number 1, rope number 2 attached to some seating. Okay? To a seating. Then you have the robots, traffic lights like this. So we've been asked to say, if this angle is 37 degrees, even this angle is 53 degrees, can you find T1, T2, and T3? The tension in rope number 1, the tension in rope number 2, and tension in rope number 3. How do you do so? The first thing that you're supposed to do is come up with a free body diagram. This is the free body diagram that we came up with. Then we have to resolve whatever force is at an angle. You get it, right? So we resolved. So for us to resolve T1, we can resolve the way we resolve in vectors. So we can still resolve here. Even here, you can resolve this one, we can resolve it like that, even that one. Okay? Then this T3 that you see here is the weight over this thing. So this is what we have here. So now, we are going to come up with equations. How are we going to come up with equations? The equations will be, because this thing is not moving, it's static, it's not moving. So we are going to say, whatever this force, which is going to the left, should be equal to the force going to the right. So we can equate the two, because this thing is not moving, and these two things are, get it? So that's how we said T1 was 37 is equal to T2 that. So we came up with equation number 1. by that principle. Then we said whatever forces are going up should be equal to whatever forces are going down. So the forces that are going up, we have this force and that force. So we said T1 sine 37 plus T2 sine 53 should be equal to the force which is going down, which is T3, right? And this force is what? 100 newtons. So we are going to have 100 newtons here. You get it? So we are going to have two equations. This one, we don't know this, we don't know that. T1 and T2, we don't know those two. Even here, we don't know T1 and T2. So these two are the equations that we are going to work with. So we can solve them simultaneously so that we can have T1 and T2. So after we solve them simultaneously, whatever we've been doing here is just to solve these two equations simultaneously. You get it, right? So we are getting our T2 as 79.49 newtons. You get it, right? Yeah, now you are with us, right? Okay, so we made T1 the subject to the formula. So using this formula, we can substitute our 79.49 there, right? Meaning that we are going to have 100 minus 0.08, supposed to be 0.80 T2, which is 79.49 like this, then divided by what? 0.61. Okay, so this will give us our T1. So our T1 will be equal to, so can someone punch everything there so that we see what we are going to have? Huh? What's the answer? 95? 60.7. So 60.7 what? Newtons. So this will be our T1. What's our T3? Our T3, from the beginning we said our T3, this is the tension in this rope, okay? And that tension is equal to the weight of this thing. So we said the weight is what? 100 newtons. So our T3 will be 100 newtons. That's 8 marks. So when you are dealing with statics and dynamics, just be sure, or here, you have to pay attention to how you are doing your simultaneous equations. Most of the times you are going to find that you are going to deal with simultaneous equations. So it's very important for you to do so. Any other questions before we can move to the next question? Any other question? No question. Okay. Go to the portal, download the paper. It should be 2023 session. 2023 session. You can just download so that we can just read the question and we can start answering. We are running out of time. Okay. Hope this is even visible. It's visible. Yeah, it's visible. It's visible. Right. So go to the portal, downloads PH110 session, no? PH110 session 2023. So that we can do a question from there. Let me just check. Let me just check. So you can just go there and download. How many have downloaded? Have you downloaded? Or tamkweta ma bundles? Okay. So go to past papers, then look for PH110. Yeah, 2023 session. PH110 sessional. So number 25. So number 25. So you can just download that one. Question number, okay, go to question 3, question 3C. Question 3C. Question 3C. Go to question 3C. Okay. So this is similar to what you have in your tutorial sheet. This question, similar to what you have in your tutorial sheet. Hopefully, at this point, you are able to answer the first one. The first question, where you have two masses, that one and that one, you're able to answer that one. I'm interested in this one. Okay, so it's saying, consider the situation in figure 3.2. Okay, can I rub this? Can't even rub this, I think. Just that you. Okay, so let me draw the system that we have. So here's the system that we have. We have this. Then we have how many newtons? 800, right? 800 newtons. Can copy that question, copy it in your book so that you see what's happening. 40 degrees. Then here we have 3/4L. Okay. So it's attached there. Then we have this. Okay. What is the first question talking about? The first one? What is it saying? What are we trying to find? Yes, what are the two conditions of static equilibrium? Two conditions of static equilibrium. You don't know. You don't know. I'm job. It's your homework. What are the two conditions?
Some of the external forces must equal to 0.
Yeah. What else?
Then the sum of them.
Number one, in simple ways, or in simple words, we can say forces must balance. External forces balance, even moments. Moments, the clockwise moment and the other moments, the anti-clockwise moment should be what? Should be equal. So this is just in general. Go to your books and learn the one that you have there, but that's the thing. Number one, whenever you're dealing with statics like this one is static. Okay, so number one, forces must balance. All the forces, all the external forces should balance. Okay, so the forces going upwards should balance with the forces going downwards. The forces going to your right should balance up with the forces going to your left. Then the moments, you know what moment is, right? A moment of a force. Let's say we have a piece of wood here. Then we have a pivot here. Okay, there's a distance between this and that. Also a distance between this and that. So moment, this thing can either go in this direction, okay, like this, or it can go in the other direction, right? So this, what do we call this? Going like that? What do we call it? It's clockwise, right? Like the way the clock moves. Then anti-clockwise like that. So the moments going downwards like that one, and the moments going in the other direction should be equal. We are going to see how we can apply that one there. Okay. So B, what is B talking about? B, what is it saying? Free body diagram. Yes, draw the free body diagram. You have a minute. Draw the free body diagram. You have a minute to draw the free body diagram. You can draw it. It's very simple. No other test has been confirmed so far. Arastapo confirmed on the test. Oh, meaning that next week or this week you won't have any tests. Good. Right. Let me just. Okay. You're done? Let us draw the free body diagram together. Okay. We'll go through together. What is the, after the free body diagram, what are we expected to find? What do we want to find after the free body diagram? Huh? The tension. Okay. So let us start. How are we going to come up with the free body diagram? The free body diagram. So the first thing, we are going to draw this. Okay. I don't know whether it's some metallic object or maybe a piece of wood, but let's say it's a piece of wood, right? What force is acting here at the end is what? 800 newtons. So at the very end here, you're going to draw like that one, because here, this is the force, right? Yes, so it's going downwards like that one. So this will be our 800 what? Newtons. Then again, from here, we have a rock, okay? So it's going in that direction, and what do we have? It's, we can just say it's T, right? So this is T. And from here, from this point, from the wall to there, what do we have? What do we have? We have, what's this? 3 over what? Over 4L, right? What else do we have? Apart from that one. What else have we been given in the question? What else have we been given in the question? What else? Have we been given anything? Can someone read the question for me? A uniform force over 600 newtons. Okay, so we are saying, oh, can you just read the entire question? The entire question. Can you read the entire question so that we understand it? Just read through the entire question. What is it saying? We have this situation. Okay. Where is P? It's here, right? Okay. We are done with that one. Then number 3. All right. So from the question, we have this, but there is wait saying a uniform force. So here, what are we going to have? That force for this thing is what? So how many newtons? How many? 600, right? Sometimes they can give you the mass of this, okay? This object here, they can give you the mass. Then you are supposed to just say weight is equal to what? Mg. But in this case, they have already calculated what? Your weight. Now, it's very important because this thing is uniform. It means that the distance from where? From here up to this point here is half L. From this point, from P up to this last point is what? It's L. Okay? So sometimes they can give you the length, or they will just say this is L. Then from here up to this point where the tension is starting from, okay, is what? 3 over 4L. What's 3 over 4? What's 3 over 4? 0. What? 0.75, right? 0.75 what? L. So from here up to here, it's from here up to here, it's 3 over 4L. Then from here up to here, we have what? L. From here up to here, we have what? We have 600. If you went through the notes, that question with a ladder, what are you supposed to do? Number 1, you're supposed to say, okay, if this is the ladder that you have, number 1, the first thing that will take effect will be the weight of the what? Of the ladder. You get it? So even the weight of this thing is supposed to be put into consideration. So the weight of this object that we have here should be put into consideration. And if it's uniform, it should come from the center, which is half. half what? L. It wasn't given here, but you're supposed to put it here. That's the free body diagram. That's the free body diagram that we have. Get the point, right? Yes. This is the free body diagram that we have, and we have to find, what are we trying to find? We have to find the tension. We have to find T. What are we going to apply? Are we going to say all forces are equal to 0 or all the moments? Okay, the anti-clockwise, we can say it's either torque or what? Or moment, still the same, right? Yes. So in this case, okay, you, depending on what you've been told to find, here we have only been told to find what? The tension. But depending on what you've been told to find, these are the two situations that you will always come across when you are answering such a question. You need to understand them. Get it right? Yes. So in this case, what we have here, okay? For the first one, all the forces should be equal, right? Meaning that the upward forces and the downward forces should be what? Should be equal. You get it right? Yes. Then for this one, the moment, if this is the pivot here, okay? Let's say this is the pivot, and then there's a force like that, and then there's that other force, and then there's this other force. What are we supposed to know here? We are, in terms of the torque, remember that torque is equal to what? Force times distance is the same as moment. Moment of force. Torque is the same as moment, which is force times what? Force times distance, right? Yeah. So all the forces, if this is the pivot, okay, if this is the pivot, then all the forces going downwards, okay, if we multiply by their respective distance from where the force is being applied to the pivot, if we multiply those that are going downwards and we add them, they should be equal to those that are going upwards. You get it? Before we do that, let us, here there is an angle. What angle is there? There's supposed to be an angle. It's what? 40 degrees. So we can resolve this, right? So if this is 40, it means that this will be T what? T what? Is it sine or cos? Sine, because it's opposite. So we are going to have sine what? 40. Then we are going to have another force, okay, which will be T what? T cos 40 like that. You get it, right? So the first thing that you're supposed to do is resolve. Now there are rules when you are applying the what? The moment. Okay, because we have just too many forces. Again, here you can have two forces. When you have the pivot like this, you are going to have two forces. One will be going up, the other one will be going down. So we can have a force like that, even a force going in the other direction like that. Get it? We can name this force going up to say, okay, this is force which is vertical, FB. Then this one is force which is going in this other direction. So you see the forces that we have. Now we have to choose the forces that we are going to apply. You get it? Yes. So in this case, what are we going to do? We are going to say, let us look at the forces that can cause this thing to move about this point here. You get it? It's like this. If I have this this marker here, okay, then there is a force which is going down like that one. Okay. So if I have any force, I can put any force here. Okay. Let's say I have this. This hope is gonna wake. Okay, so this is how the situation is. So there are two, I'm saying there are two things here that we have to put into consideration. There's this, all the forces should be balanced. Then the other one says all the torques should be what? Should be balanced, right? Yes. So when you are dealing with the moment, because such question will always want you to apply the moment, right? Yes. So if I have this, you need to know that moment deals with this object going in the clockwise direction or in the anti-clockwise what direction, right? So if I have this, then let's say this is the 800 newtons. Okay, you see how this thing is moving. I'm not the one moving, but because this is the force, it will be moving where? Going downwards. So this will cause a what? A moment. You get it, right? Yes. If I have this force going upwards, let's say I'm pulling this. So if I pull, what's happening? This thing is still moving. So there is an impact. This force will cause this thing to go in this direction. Okay, it's either clockwise or anti-clockwise. So whenever you are applying this, the moment of force, always try to see which forces will apply, because there are just too many forces and not all forces applies to moments. Get the point, right? Yes. Now, in this case, let us mark. We said this first force, is it going to apply? Is it going to cause this thing to have a moment? Yes, right? So this one, yes. This force, if we pull like that, this one, is it going to apply? Huh? If I pull, the way I was pulling, this is the object that we have, and then we have this T sign port I'm pulling. This one is making a moment, right? By moment, we are just saying it's moving like a clock, eh? Yes. So this one will be also applicable. What else? We have this one, which is 600 newtons, this force, right? Is it going to be applicable like this? So this force is causing this to go. So even this one will be applicable, right? There is also another force. Remember that this force that we have here, we resolved it in two directions. We have this one and this other one, okay? So we are saying this one will be applicable. And then there is another force which is moving along this piece. You get it? So it's more like there is this, then I'm trying to push because this force is moving like that. So if I push, is it causing this thing to move in this direction or the other direction? Not really, right? So this force, whatever force is moving within the object, this object is not applicable to moments. So we just ignore them. Get the point, right? Yes. At this point here, at the pivot, there are two forces. One is going up and another one is going in this direction, right? Yes. We say that at any pivot, you are going to have two forces. Keep that in mind. So we have F, it's vertical going up, then this one F, horizontal going in this direction, right? Now, if I apply a force at this point here, which force is going to be applicable? Which force? This force going up or this force going downwards or in the horizontal direction? Which one will cause this thing to move? Huh? The one upwards. What about the one going in this direction? So if it's along this thing, it means that we automatically cancel it out, right? Yes. So if this is what we have, if I have this, right? Then I'm applying a force. I'm applying at the pivot here. If I try to apply at the pivot, is it moving? Is it moving in this direction or the other direction? Is it moving? This is a pivot, right? A paper pivot. Remember that this force, 800 newtons, is more like this. So it's moving, right? This one, if we say we resolve it, there's one which will be pulling, so it will be moving, right? Now I'm pushing here at the pivot. You said this one will cause the thing to move either this way or the other way, but I'm pushing. Is it moving? It's not moving. You can try it if you want. Or maybe you were thinking I'm holding it. No, I'm pushing, trying to push. So you find that at the pivot, these forces at the pivot, all the forces at the pivot will be ignored because they don't cause this thing to move either in this direction or the other direction. That's moments. So we have found out that only three forces will be applicable. Get the point, right? So now back to this formula. Okay, we are saying torque is equal to force times distance. So what forces will cause this thing to go in this direction? This is clockwise, right? And so this is clockwise. Which forces? This one and that force, right? So if we say the torque going in this direction, let's say clockwise, right, should be equal to the torque going in which direction? The other direction, right? So it doesn't really matter how you write this, but so long as you know what you are talking about. So because the formula is force times distance, if we take a look at 600, this one, we are going to multiply this 600 multiplied by the distance from here up to here. We say this what? Here up to here, it's what? Half L. So this is what we are going to have. Half, then L. This is the first force. Because both of these forces are going to cause this to move in the clockwise direction, we are going to add even where? This one. It will be 800. Now, the distance from here up to there is what? It's L, right? Yes, you've been given the distance, so you write your L there. Then this will be equal to, yes, please. Yes, please. Around 18, 20, somewhere. Yeah. Which part? This part? This part. You know where this half L is coming from? Even this L? Okay. So the distance between where this force is, which is 600 newtons, and this pivot is what we've been given as half L. You know where it was coming from? We were not initially given this. Okay, we weren't given this, so we had to put it here because number one, this stick here, let's say this is a stick, this stick has a weight, right? So that weight, we are going to go to the center of the mass. That's where the weight will come from. You get it? And it was given to be 600 what? Newtons. So from here up to here, in the question, if you look at the question, it was saying it's L from here up to here. So this entire thing is L. So since this is at the center, we can just say L divided by 2. So that's where we are going to get our half L. So from here up to where the 600 force is, we are going to have half L. Then from here to here, we are going to have L. Then there's this force here. We were given 3 over 4 L for this force that we resolved. You get it? Yes. So considering all of that, this 600, we are multiplying it by half what? L. So 600 multiplied by what? By this gives us the moment caused by this 600 force. We go to this other force. So we are going to say from here to here is what? L. L multiplied by 800. So L multiplied by 800. We are multiplying there. Should be equal to, because these forces are causing this to go downwards. So we are going to equate it to the forces causing this thing to go in the other direction. You get it, right? Yes. Yes, please.
Isn't this indicating the descent?
Let me see.
Getting the center of mass from here.
When you've been given a diagram in physics, it's not always up to scale. You get it? This is why they have labeled this to say 3 over 4 L or 3 L over 4. It's the same thing. So you don't have to look at the diagram and say, okay, I'm assuming that this is the same. Get the point, right? Yes, that's how the thing is. So the center 3 over 4, because 3 over 4 is somewhere 0.75, 0.75. So 0.5, which one comes first? 0.5. So this is why we have this thing here and the other one here. 0.5 comes first before 0.75. Get the point, right? Yes. So yes, the diagram there, and it's showing that this rope is starting somewhere from the center, but remember that we've been given the measurements. So you have to take the measurement and not what you see. Get it right? Yes. So this, because we have dealt with whatever is pulling this and is causing this stick to go downwards, what about the forces that will cause this stick to go upwards? How many forces do we have? We have this, right? So we are going to say this force is what? T sine what? T sine 40, right? Remember this equation is starting from here. T sine 40 multiplied by what? This distance from here up to here. What do we have? We have this distance according to the diagram, which is 3 over 4 L. You get it? So if they have told you that the length of this entire thing is 1 meter, our L can be substituted by 1. You get the point, right? Yes. So this is the equation that we are going to have. Then after this, can we see what's common here? What's common? Can we see anything common? We can get rid of the L, right? Yes, we can just say this like that. We multiply by 1 over L, like that. Okay? So if we multiply throughout, this multiplied by that, we are going to just cancel that one, and we are going to have 600 times half. Then here plus 800. Now we have cancelled out because this cancels out with that one. Then here we are going to have T sine 40 times 3 over 4. How many variables do we have? The unknown variables is what? T. This is what we are looking for, right? So can you punch this on the calculator? What are you getting after you punch that? What are you getting? What are you getting? After you punch that one. What are you getting? Is what? 1,100. 1,100. Like this? Okay? then it's supposed to be equal to what? What's sine 40 multiplied by 3 over 4? Sine 40 multiplied by 3 over 4. What are you getting? So what? 0.48. Okay? See, so we can say 0.48 here. Even here we can say 0.48. Then we cancel out that one. What are we going to have as our final answer? Yes, please. Huh? Where? Here. What are we getting here? 0.5? When you punch sine 40 multiplied by 3 over 4, that's what you are getting. Eh? Pancha. There must special angles there. There are special angles. You can just punch. So what are you getting for T? T is what? Panjani, you have calculators. Nijinga? Eh? 2.3. We are dividing this. 1100 divided by 0.48. 2000 and what? 91 newtons. Okay. So that's our T. Any question? $91 or 81? Huh? It should be 0.5. Let me see. I didn't marry Janzi. 0.45 or 48. 0.4, or maybe let me see. Sine 40 multiplied by what? By 3 over 4, right? 3 Veda engineering calculator over can't see over. Gentlemen, my calculator is this cash. Okay, so you're saying 3 over 4, 4.75 multiplied by sine 40. Sine 40, right? It's 0.482. 0.482. Yeah, 0.482.
Is your only
Okay, put a 2 there. Put a 2 for it to be more approximate, or for it to be closer to the answer. Put a 2, at least three decimal places. So this one will change. What are you getting? Just punch your calculator right here. Okay, what are you getting? 2 to what? If you say 0.1100 divided by 0.48, then we have a 2 here. What are you getting? 2, 82. So we can have 82, and this is closer to the actual answer. So there you have it. Right. Any question? Any question? No question? Okay. Let's see if we can do another question. Okay, another question. We can do a question on ladders. Can we do that one? Same concept. We can do that one. Go to the radical notes. I'll just go through fast. And I want to point out a few things. Go to statics part. Statics. What did I put there? What did I label it as? That's where the question is. Actually, the question is already answered. So I just want to explain something so that we can do another question and we can wrap up the lesson. Okay. So statics part, go to statics. There's the introduction. There are about three documents there. Number 14. Say number 14. Physics, statics, and dynamics. You can download that one and open it. Okay. I think this question is also in your tutorial sheet. The ladders question, right? Where you have a ladder, so leaning against the wall. Did you manage to answer it? Huh? Madisanga. Hopefully. The answer is already there. The answer is already there. Okay. I can rub. You rub. Yeah. It does mean the whiteboard is clean or something. This thing is not working. Okay, so if you go down there, you'll find that there are ladders there. Okay, we have some questions, to my simple questions and answers. You find that there are ladders. There are two questions on ladders. One coming from your tutorial sheet, okay, which was saying a uniform ladder denoted by that one. You can see the ladder, this ladder, this one. This is the ladder I'm talking about. This one. It's the ladder I'm talking about. Okay. So a uniform ladder denoted by that figure. So we have a ladder. Now this ladder is like this. We have this. So this is the ladder, and we have 53 degrees like this. Then we have from there, from here up to here. We have how many? 5 meters, 5.0 meters. Okay. So here you are going to apply two things. Number one, you're going to apply the first condition, which is all forces in the y direction should be equal to 0. All forces in the x should be equal to 0. Also, all the moments, okay, the anti-clockwise moments, when I write this the same as top, right, or moment, should be equal to the other one should be pointing in the other direction. So this is what you are going to apply when it comes to the ladder, right? So here's the thing. It's saying a uniform ladder denoted in this figure. So this is the figure, okay? Is 5.0 meters long and weighs 400 newtons. So the weight for this is what? Is 400 newtons. So the moment you just hear of weights, go to the center of the ladder because they are saying it's uniform. So go there, when you are writing or when you are coming up with the free body diagram, go to the center and immediately you are going to say, here, you are going to have what? 400 newtons. Okay? So sometimes you can be given the mass of the ladder. All you have to do is you say mg, right? Mass multiplied by 9.81 should give you what you are supposed to have here. Get the point, right? And then, what are you going to do? Here, whenever you are taking the moments, you have to choose where the pivot will be. Okay? Where will be the pivot? Remember what we had for this one. We said that if we have a moment, there should always be a pivot, right? So even in this case, the ladder will have a pivot. And most of the times, if not always, we put it down here because it will cancel out the most of the forces here when we are dealing with the moment. So this is where we are going to put our pivot. So our distance when coming up with the moments, what are we going to be doing? We'll be saying, okay, the moment will be from here up to where? Up to there, right? So this is the distance that we'll be taking. You get it, right? Yes. What else? What else are we going to do? What do we want to find first? I didn't finish the question. I didn't finish reading the question. Let me finish up the question. So the question is saying, okay, the inclination angle between the ladder and the rough floor is 53 degrees. So here we have 53 degrees. Okay? Yeah. Now find the reaction forces from the floor and from the wall on the ladder and the static friction coefficient at the interface of the ladder with the floor that prevents the ladder from slipping. Okay, so if this is in equilibrium, what's going to happen? It won't be moving, right? Yes. Now, this ladder will always want to slip. So that it falls. Now, what's preventing this ladder from falling? It's friction. Okay, because this ladder now get up like this one, this thing can only move, the ladder will move like that, and that will cause you to fall. But now you are not falling, so it means that if this tends to go in this direction, it means that the friction will want to go in that direction, and you are going to have what? Static friction. So that's where you're supposed to start your calculations from here. You need to identify that at this point here you have two friction or two forces. Now you have this force, right? The friction, the static friction. So it will be opposing the whatever force will try to make this thing to slip like that. You get it? Now here, this is a surface. We said that whenever you have a surface will always apply a force on an object, right? What do we call that force? We call it the normal force. So there will be a normal force, and we can say a normal one. Why are we saying one? Because there is another normal force. Here, this is a wall, right? So since this is the wall, there is another force that will try to do what? To push this ladder so that it falls in the other direction. Now, because this is in equilibrium, there is a balance of forces, right? Yes, so it won't fall. So this one will be what? Will be N2. Get the point, right? So if they tell you to say, okay, there is an electrician who's trying to go somewhere up there, you also have to put the mass there, and you are going to say, oh, you have the weight of the electrician, like that one, because there are two questions there in the notes. So you can see those two scenarios. All right. So in this case, if they tell you to say, can you find the two reaction forces? They are talking about this one, this force and that force. You get it, right? Yes. Then what else can they tell you to find? They have told us to find what? The coefficient of static friction. Okay. So the coefficient of static friction will come from where? From this. So that's the analysis that you need to make. You get it, huh? Yes. Now, can we start solving? Or maybe you can go through. Should we solve this one? You can solve. Okay, you have 2 minutes to solve. I've given you the free body diagram. This is the free body diagram. Can you find N1 and N2? Okay, you have 2 minutes to brainstorm what we are going to do. Or if you want, you can go through the notes. If you have already opened the notes, you can go through the notes so that you have an idea, because everything is well explained there. Everything is well explained. Okay, how we can find N2? Question in Italy. It's long. It's very, very long. Okay. Okay. Have you gone through? Beat them. So here's the thing. Let us start. If we have this, let us look at the main forces that we have. Okay. What forces do we have? We have N1, N2, and this other force, right? So we can say we have some forces going in this direction, right? And do we have any force going in this direction? Yes, we do. This one. I bet you can't see this one. There's a force going in this direction. So if this force, even that force, this force going in this direction. So you find that these two forces are balancing up. You get it? Because this one will try to push it to go to the other side, even this one to the other side. So there is a balance here. So we are going to say forces in the what? Summation of forces in the X should be equal to what? Is this thing moving? Is it moving or not moving? Is the ladder moving or not moving? It's not moving, right? So is there any acceleration? No. So you are going to put 0 here, right? Yes. You have a question? Yes, please. You have a question? Oh, okay. That's not the question. Okay, we can move on. So you are saying that all the forces in the x-axis should be equal to 0, right? Meaning that this force should be equal to this force, because these are the only forces that are going in the x-axis, right? So we are going to say Fs should be equal to what? N2. This will be our first equation. Get it, right? Yes. Now, what else do we have? What else do we have? We have these two forces. There's one going downwards, and we have another one going up. Do we have such? We have this one. So forces in the what? In the y. Summation of forces in the y will be equal to 0. What forces do we have in the y-axis? What forces do we have? According to the diagram, what forces do we have there? There's 400 newtons. What else? There is this force, which is N1, right? So we are going to say N1 should be equal to the force going down, right? Which is what? 400 newtons. So we have found N1. So far, N1. Any questions so far? This is the analysis. Huh? Where? This one. So we are saying we have this. We have two forces. We have N1. You know that this is N1, right? Then we have this one. This is the static friction, which is holding this thing so that it doesn't fall. Okay, so we are saying that the forces in the x-axis, so whatever forces are facing in this direction should be equal to the forces going in this direction, right? So in this direction we have Fs, in going in that direction we have this. So these two are equal. So this is what we have written here. Now for the forces in the y direction, this force should be equal to this other force, because we only have one force, N1, which is pointing upwards, and this other force which is pointing where? Downwards, like this. So this is why we can equate this, and that's how we are coming up with N1. Okay? Yeah. So after we are done with that one, what else can we find here? What else can we find? Have we been given new? Not read. So if you exhaust, here is how things work. After you exhaust this one and that one, go to the moments. You get it? So after you are done with the statics part, this one, where the forces are equal, the forces, the summation will be equal to 0. Go to now the moments. This is how such questions work, always. So now we can go to that. We can go to that. We can just write it here on this part. So we are going to say moments. Moments, meaning that the moments going in that direction should be equal to the moments going this direction. Now, when you are dealing with moments, okay, you have to resolve this. That's the first thing. Resolve the forces at an angle. Because do you know what happens to moments when we are dealing with moments? If I have, let's say I have this, right? If I want to, if let's say we have this and we have that. If I say, can I pick a force between F1 and F2 that I can use directly, I'm going to pick F2 because it's at 90 degrees. So the force that you are picking here, that you are going to pick, should be at 90 degrees. This is why we normally do what? We normally resolve this so that this force becomes at 90 degrees with this. You get the point, right? So in this case, if you have a ladder like this one, you can't pick any force. Okay, so you have to resolve. If I resolve my N2 here, I can pick this force, right? Because it's at 90 degrees with this. You get this, right? Yes, with the stick. And again, I'm going to do what? We ignore this. Why? Because even if I pull here, it won't cause, I push it here. It won't cause this ladder to go this direction or the other direction. Okay, remember that rule where we said all the forces that are going through this stick here that we have here, or the ladder that we have, should not be considered because they don't apply. You get it, right? Yes. So in this case, we have to resolve. What are we resolving? We can resolve this. So this angle is equal to this angle, right? So this angle will be what? This angle will be what? Huh? Oh, this angle will be 53. So this force will be what? 400 what? Is it cos or sine? Cos, because sine will be this other one, which is going in this direction. That you know. So cos what? Cos 53. You get it, right? Even this one, how are the angles going to be? This angle, remember that Z property, that one. This angle is equal to that. Look at this. This. If I have this angle, it means that it's equal to that angle. You get it, right? So 53. So if you have forgotten Ama angle properties, go back to them. 53 degrees. Okay. So if I want to find this one, it will be N2 what? Sine 53. You get the point. Now we can apply the moments. Here we have Gamma forces. At the pivot, we have forces Fs and what? N1. But since this is at the pivot, all these forces won't apply because if I push at this point, it won't cause this to rotate like that. You get it, right? Yes. So this will be cancelled. So what will be applicable? Force number one that will be applicable. Remember, we are getting forces that will be what? At 90 degrees. So this one will be applicable. Even this one will be applicable. Do you have any other force that should be applicable? No other force? So only those two, right? So as a result, we can say, because this force, if I pull, it will cause this to go down. If I pull like that, it will cause this to go like that. So I'm going to say 400 cos what? Cos 53. From here up to here, it's what? It's half, right? Which is 0.5. Have we been given the length of the entire ladder from the question? It's what? It's 5, right? So we are going to have 2.5 there, right? So we are going to multiply this by 2.5. Then it should be equal to what? This one, which is N2 sine 53 multiplied by what? Multiplied by 5. So can you find N2? Because N2 is the only variable that we don't know. It's 40 cos 53 multiplied by 2.5 divided by sine 53 multiplied by 5. This will be our N2. What are we getting? Yes, please. The 2.5, where is it coming from? Where is our 2? This is 2.5. Do you know where this is coming from? Yes. It's coming from where? From this, right? So we say moment is equal to force times distance, right? So basically what we are saying is if we have moment is equal to force times distance, the force that we have, this force, we are supposed to multiply it by the distance from where? From the pivot. From here up to here is what? It's 5 meters. So 5 divided by 2 is 2.5. That's where our 2.5 is coming from. You get it, right? Yes. So that's what we have. What will be our N2? What's our N2? N2 is what? N2, what are we having for N2? N2 will be equal to what? Sangenka N2. And after we find N2, we can find Fs using this. So N2 will be equal to Fs. Then we know that Fs is equal to mu K, what? Mu Sn, right? Mu Sn. What are you going to have? Namnazanga? We haven't answered yet. What are we having? What are we having? What's N2? After you punch, what are we having for N2? Chinga? 150.71. So 150.71. Our N2 is 150.71. That will be our N2. This one. The board is a bit messy. Unfortunately, we can't rub. So N1 is what? Remember, from here we said N1 is equal to 400 newtons, right? Remember the units. After you are done with everything, Fs will be equal to what? Fs will be equal to 150.71. Then, using this formula, we are able to find mu s. So mu s is equal to Fs over n. What's our n? Now the n that we are going to get is n1. So it will be n1. So Fs, what's our Fs? It's 150.71 divided by 400. This should give us our mu s, like that. What are we getting? What are we getting? But you are following that? Yes. N1? Fs? Okay. How did I get Fs? This equation, Fs is equal to N2. So we have answered to say we have found N2 to be 150.71. So our Fs will be equal to 150.71. As simple as that. This is where we're coming from, so you can just get that. And we can plug it in here. Then N1 here, you know what N1 is? N1 is this. We answered it by saying all the forces in the y-axis should be equal to 0. So we said all the forces that are in the y. So this force and that force should be equal. That's how we came up with 400. So this is how we came up with that. Then Fs, I'm just from explaining. Then mu s, we are saying if you have this Fs, okay, the frictional force should be equal to mu s, then multiplied by the normal force. So we have found our normal force to be what? To be 400. Then what else? Our Fs to be what? This. So using the formula, we can make this the subject of the formula, and we can actually find mu s, which should be less than 1. What are we going to get? What are we going to get? Is what? 0.38. 0.38. This one doesn't have units. So the coefficient of static friction. You get it, Cap? Yes. Any questions? So that's how you deal with ladders. Ladders, whatever the systems that we've talked about, almost everything. Okay? So if you have something like this, we are done with that question. I want to just explain a bit about this. If you have something like this, so the thing is, let's say this one is what the question is. Can you read out that question, Moon? That question that you sent. Just want to point out a few things so that we can wrap up this and we can start our term 2 again tomorrow. What is the question talking about? What should be the maximum? What? Of m, the mass. Okay, so this is a static friction. This is a static question. If I want to draw, it's all about how you draw your free body diagram, right? So if I want to draw my free body diagram for this one, I'm going to say I'm going to have normal force, right? Then I'm going to have mg. What mass do they want? This one or this one? This one? This one. They have given this one. Okay, so how you draw your free body diagram matters. Okay. So here, this will be your tension, right? So you are going to have your tension. Here you are going to have Fs, because this thing is not moving. Is it moving? It's not moving. So it's static like this one. So we are using Fs. Okay. Then here we can draw the free body diagram because there's a weight, which is mg, and then there's this force going upward, which is the tension like this, right? So what you have to do is, normally we say, okay, acceleration, this thing is going in this direction, right? That's what we are used to. Now, whereby this thing is not moving, it means that there's a balance in terms of forces. So if you say summation of forces in the x is equal to ma. This is what we normally do when this is moving, right? So if it's not moving, means that our acceleration is 0, right? So the only thing that will change is, instead of using ma here, we are going to say the summation of forces in the x for this free body diagram will be equal to 0. That is the only thing that will change, and you are going to have your answer after you apply everything that you have to apply on the free body diagram. Get it? So only that part. Then you are going to have that answer. Is there? I saw something similar to an answer. Is that the actual answer? That is on the same question that you sent, or you stopped solving it? Okay, maybe I just today I'm a bit busy today, so we'll see if I can solve through and I can send this to you. But that's what I wanted to point out. Otherwise, this is where we end. Any questions? No questions. No question. Eh? Okay.